So the next thing we want to talk about is what are orbitals? What are these things that we've been talking about in terms of electron orbitals and where they are and how they are and what they're quantified as? Well, there's a couple of different ways that we can describe orbitals. I'm going to just define them as a region in space around the nucleus of an atom that has a probability of finding those electrons in that area. It's usually 90%, and so when we talk about an orbital and we define electrons as being in that orbital, what we're saying is that there's a 90% chance of the time that, or 90% chance that anytime you look, you will find those electrons within that orbital. And so that's really the long and the short of it. Okay, so there are regions in space where electrons spend their time, basically. Okay, now we have 4 different orbitals that we have to worry about. The first one we have is an s orbital, and s orbitals are spherical, which is why they have the little spheres right there for you. They increase in size as they go further away from the nucleus. You can think of them as like Russian nesting dolls. Ping pong ball inside a softball, inside a volleyball, etc., etc., etc. And so they just get bigger and they're centered around the nucleus. Okay, so each of the s orbital can hold 2 electrons. So that's what we care about when we're talking about electron configurations and all of that other stuff. And so that's where we're at with that. The next one we're going to talk about are p orbitals. And p orbitals are figure 8 shaped. Each p orbital, each energy level p orbital has got 3 subshells within it. Each of those subshells has 2 separate lobes. So each lobe can hold an electron for a total of 6 electrons for a possible p orbital of a certain energy level. And so why are there 3 of them? There's 3 figure 8s. So we've got a figure 8 vertically, we've got a figure 8 to the x, and then we've got a figure 8 to the y. Okay, so these 2 are 90 degrees apart, and this is 90 degrees apart from them. And so if you were to couple all of these together, and my drawing is going to be garbage because you guys know that's how I draw, but that's my vertical, that's my one that's in the plane of my board here, and then this one is going to be sticking in the front and the back of the board, which, like I said, is garbage. But if we put them all together, that's what it would look like. So you could see if you took this image that's nice, not my drawing, and you mushed it together, you would see that you would end up with p orbitals that would look kind of like that. Okay, so those are the p orbitals. Now, the next ones we're going to talk about are the d orbitals. And unfortunately, my lovely drawing that I had for you disappeared. It got eaten. Okay, so they're the d orbitals. Now, there are no convenient way to describe d orbitals. I'll try and draw a really awesome sketch. You can laugh, and that's fine. But each energy level d orbital has got 5 subshells in it. Each of those 5 subshells can hold 2 electrons for a total of 10 electrons held inside each of the energy level d orbitals. Okay, now if we're going to pretend to draw them, they're going to be horrible, but whatever. So you could imagine something that looks kind of like our p orbital, sorta. Okay, so imagine those are the same, because you know a real artist could do that. I can't. That's fine. Okay, so now a d orbital is going to look kind of like that, sort of like a butterfly according to this drawing, but whatever. Now there's 4 that look like this. They're just rotated in alternate directions. Okay, so there'd be one in the plane of a y-axis, there'd be one in the plane of the x-axis, there'd be one in the plane of the x, y, the z-axis. So we've got 3 there, and then there would be one laid flat where these would be along the x and the y, and then there would be one where this would be laid flat and rotated in between the x and the y axes. I'm never going to ask you to make that, but just they look like a funky clover leaf. Okay, then the other one that doesn't look like that at all is going to be kind of so here's a ring, and go ahead, you guys know that I'm not an artist. So this one is going to look kind of like a ring, and so my nucleus, or my axes, the nucleus would be right here hidden away in the middle. And so It kind of looks like a donut with two donut holes floating above and below it. It's the easiest way to say it. So yeah, that's what I got. And yeah, so 4 of those, 1 of those, that gives me my total 5 d orbitals that hold a total of 10 electrons. So this can hold 2 electrons. Each of these can hold 2 electrons, and so that's where I get my number of 10 from. So again, not a great artist. I'm sorry that my picture didn't pop through when I transmitted it or converted it to PDF, but it happened. And, you know, we will live through this. Hey, that one's there, though. Sweet. Oh, there it is. It just moved it. Ah, cool. That makes me happy. Okay, so there's my incredible artistry. So this is what I was trying to draw. This is the 4 lobes of the d orbital, and you can see this one is on the y-axis, so it's on the z and the y. This one is on the x and the z, and then this one is flat on the x and the y, but it's rotated so the lobes don't go right through the x and the y. And this one is flat on the x and the y, but it's rotated 45 degrees so that the lobes are on the axis. And this is the donut hole thing that I was talking about. So yay, it worked. Then the last one we're going to talk about are the f orbitals. And so your f orbitals, there are 7 of them. Each of those 7 orbitals can hold 2 electrons for a total of 14. And I'll just jump over here so you can see me. There we go. So there's a total of 14 electrons per energy level. And if you actually look at the diagram, there's no way that I could conceivably draw this, and I'm not even going to pretend that it's a possibility. You don't need to know what they are. I guess the easiest way to think about them to me would be a stack of 6 jelly beans, and it's just kind of like rubber banded together, and you just rotate it in space a whole bunch of different times, at least until we get to the funny looking one here with the double donut holes. Now, I'm never going to ask you to draw those. It doesn't matter. You don't need to know that. But if you're curious about it, you want to look at it, that's what it is. Okay? Now, the next thing that we're going to talk about after this is going to be electron configurations. Electron configurations from the periodic table. And I think that's it. Okay, and so we're going into electron configurations. And so the problem with electron configurations is I want to do that in person. So those units we're going to do in notes together in the house, and I don't even think we're really going to do notes on it. I think we're just going to do it and get it done with so that you see what's coming up. And other than that, that's pretty much it. This is this whole unit in a nutshell. It's not going to take us very long to get this one done. So awesome. See ya.